Hello everyone, this is the second part of the chapter, benzene and substituted benzenes. In this part of the chapter, we are going to talk about electrophilic aromatic substitution reactions of benzene. It can undergo 5 different electrophilic aromatic substitution reactions. The first one is halogenation. Halogenation is going to replace the hydrogen on the benzene with one of these halogens, Br, chlorine, or iodine. Nitration is going to replace the hydrogen with an NO2 group, and sulfonation is going to put a sulfonic acid group on it. Acylation is going to put an acyl group, and alkylation is going to put an R group. In all of these reactions, the mechanism is going to be exactly the same. The one thing that you have to keep in mind is the generation of the electrophile. Okay. So here is the standard reaction. Benzene, when it is reacted with an electrophile, the hydrogen in that is going to get replaced for the electrophile. Okay, so as you can see, the hydrogen is replaced with an electrophile. Okay, mechanism for this reaction. All of these reactions occur in a two-step mechanism, way. So you can see that there is a benzene molecule which, when reacted with an electrophile, it is going to generate 3 contributing resonance contributors, and a base either from the solvent or from the reaction mixture. It's going to go abstract this hydrogen and thrust these electrons back into the ring to generate the aromaticity of the molecule and finally form the product. Okay, and this reaction is going to be super fast. Okay, halogenation of benzene. What is required for the halogenation of benzene? For the halogenation of benzene, you require a Lewis acid catalyst, either FeCl3 or FeBr3. Okay, so FeCl3, a benzene molecule, when reacted with bromine in the presence of FeBr3, is going to give bromobenzene. And you do exactly the same thing for chlorination. The only thing that you will do is, instead of bromine, you will take chlorine, and you will replace the catalyst with FeCl3. Okay, and you can get chlorobenzene. Okay, now why a catalyst is required for the halogenation of benzene? So remember, when you looked into when we did the halogenation of alkene, we did not use any catalyst for the electrophilic addition. But for the electrophilic aromatic substitution of benzene, we need a catalyst. That's because benzene is a more stable compound and therefore less reactive than an alkene. And that's the reason it requires a very good electrophile. And adding the Lewis acid catalyst is going to make the bromine or chlorine into a better electrophile. Now let's see how a better electrophile is formed by adding Lewis acid catalyst. So the bromine molecule, Lewis dot structure is going to look like this. Now when reacted with a catalyst, Lewis acid catalyst, the bromine will use its lone pair of electrons to form a bond with Fe. Now, because bromine has used its lone pair of electrons to form a bond with Fe, it's going to be positively charged, and therefore this bromine right here is actually going to be a good electrophile. Okay, so now when there is a benzene molecule, this electrons can go and attack this bromine, thereby converting it into a good leaving group. This is the leaving group in the that is generated. Okay. Let's go on to the mechanism for this reaction. Okay, again, all of these mechanisms are going to be exactly similar. are going to be similar. Okay, so here is benzene, and after you convert it into a good electrophile, it's going to look like this. Now the bromine with its pi bond is going to go attack on the electrophilic bromine. Sorry, the benzene with its pi bond was going to go attack on the electrophilic bromine, and it's going to thrust those electrons onto bromine by converting into a good leaving group. And here is my leaving group, and it's going to form the carbocation, and again it's going to be in resonance with two other structures. Okay, and in the next step, the base is going to go abstract this hydrogen and put the bond back in the ring to form the double bond, or to restore the aromaticity to give bromobenzene. Okay, so in all of these reactions, you can tell that the first step is the addition of the electrophile. And in the next step, the base, either from the reaction mixture or the one that is generated from the electrophile, is going to go abstract the hydrogen. Okay, so the base abstracting the hydrogen to reform the aromatic compound, to reform the aromatic compound, aromatic ring. Okay, so this is the standard reaction that we are going to follow for the rest of the reactions as well. Okay, handling of FeBr3 and FeCl3. Okay, FeBr3 and FeCl3 reacts readily with moisture, and therefore it gets inactivated. And that's the reason you always needed to synthesize FeBr3 and FeCl3 in situ, which means in the reaction. Okay, for which you take ion fillings with bromine or chlorine, depending upon what type of halogenation you want to perform. So iron, when reacted with bromine, it's going to give FeBr3. Now let's go on to iodination. Okay, for iodination, you actually need an oxidizing agent in acidic condition. Now, what is the oxidizing agent that's commonly used? It's actually hydrogen peroxide, and the normally used acid is H2SO4. So let's write the reaction. A benzene molecule, when reacted with iodine, in the presence of H2O2 and H2SO4, is to the iodination of benzene along with the acid generated. Okay, now what is the use of the oxidizing agent here? The oxidizing agent is actually going to convert molecular iodine into an electrophile. So here is the electrophile that's generated. I plus is the electrophile that's generated. Okay, next let's go on to the second electrophilic aromatic substitution reaction, which is nitration. For nitration, we need two things. The first one is nitric acid, and the second one is H2SO4, which is going to act as a catalyst. Okay, so let's write the standard reaction. General reaction. So benzene molecule, when reacted with HNO3 in the presence of H2SO4, which is a catalyst, it's going to give nitrobenzene. Now, in all of these processes, you have to add one other step, which is the generation of the electrophile. The electrophile right here is NO2 plus. Now, how do we generate NO2 plus? Okay, it's actually generated with the use of H2SO4. The H2SO4 is actually going to protonate nitric acid, and the protonated nitric acid loses water to form NO2 plus. Let's see the reaction. So here is nitric acid. Remember, this formula for nitric acid is HNO3, and I have separated this as like this. Okay, and that reacts with H2SO4, and this is H2SO4, which is separated as HNOSO3H. Now the first step is the electrons from the oxygen is going to go attack or abstract the hydrogen from the acid to get it converted into a good leaving group. Okay, once it is good converted into a good leaving group, remember here we have water, which is actually a good leaving group. So these electrons will be going on to water, going on to oxygen, thereby generating water and the electrophile. Okay, so this is the electrophile that is used for nitration. And let's go on to the mechanism for the reaction. For the mechanism, you will take benzene with the electrophile nitro group. Again, the mechanism is going to be exactly the same. The pi bond is going to go attack the nitrogen on the nitro group, thereby forming a carbocation. And this carbocation is going to be in resonance with 3 other structures. Okay, and the base is going to come in and abstract this hydrogen. These electrons will thrust back in to reform the aromatic ring structure. Again, the base could be either from the reaction, or it could be the solvent, or it could be HSO4 minus, which is the base that is synthesized at this step. So you can see that HSO4 minus is synthesized here. So that could be the base that can go and abstract this hydrogen right here. Okay, so in all of this, you can tell that the first step is going to be the electrophile that is added to the benzene ring, and in the next step, the base comes and abstract the hydrogen, trying to reform the ring structure.